we just had 3 intensive days on MLR. What we've been doing, time series, is just an instance of multiple linear regression. Everything we just did was just MLR, just doing it for time series, okay? So I did it that way in the class on purpose. We had a day on MLR, multiple linear regression, to kind of get you the basics, and then we did 2 more intensive days of practice, and with the idea of hoping you kind of just get more depth and more understanding of doing it some more. So we've had 3 Python intense days, and we've been doing MLR, and some of you have been doing it in JUMP, which is fine. I don't care. That's fine too. But we've had, it's still MLR. It's still the very same algorithm under the hood, and understanding what the terms mean and coming up with the coefficients and doing all of that stuff. So we've had 3 good, solid days of multiple linear regression, and so that's been really good. Now we need to get back to doing some evaluating our categorical models. So when you're using regressions, you're predicting numbers. You know, how many go through the tunnel on next Tuesday? How many cars do I have to plan for going through the tunnel? How much electricity do I need to generate next month? You know, those are predicting numbers. Now we're going to do some more. We'll continue to predict numbers, but we're going to we need to do some more categorical prediction. And so we've got algorithms that are going to do more. I'm going to teach you artificial neural networks can both predict numbers and they can predict categories. Boosted trees can do numbers and categories. So we're going to do algorithms that can do both. But we're going to take a little bit of time today just to sort of like say, I need to know how to evaluate categorical prediction models and know whether I'm doing a good job. What are all these? What does recall mean? What does precision mean? You know, what does the F measure mean? Why do I care? What's a true positive? What's a false positive? So today, you know, what's the ROC curve really showing me? So today we're going to look at that because we need to kind of get our head wrapped around categorical prediction. And so let's talk about some of these ideas. And I've introduced them before. And those of you that took Dr. Keith's class, you saw them there, but you didn't spend a lot of time necessarily thinking behind the scenes as to what everything really means. So, and if you didn't take, I know I've got a handful of you in here that didn't take Dr. Keith's class. That's fine. I'll give you the good stuff right now so you can kind of like also get this stuff connected up in your head. Okay? So the first thing we're going to do is we're going to talk about the naive rule. And I talked about it once before in class. Let's do it. Let's talk about it today with an example or two, because it's an important idea. And there will be some questions in the test in the midterm where I'll ask you, apply the naive rule. Okay? So let's go back to our mushroom example, and let's assume that 30%, or let's use round numbers. Let's assume that we have poisonous ones and non-poisonous ones, and we have a sample size of 1,000, and we have 300 that are poisonous. Now, one of the things that you need to think about is what am I looking for? And sometimes it's a positive thing, and sometimes it's a negative thing. In this case, I'm looking for poisonous mushrooms. So this is my class of interest. Class of interest. Okay? If I was doing, I'm trying to find who's going to buy my cars or buy my product, my class of interest would be buyers. So sometimes my class of interest is I'm looking for something that's negative that I can't sell to my customers. And sometimes I'm looking for who will buy. You know, up here, another camp, who's going to get cancer? So that's the case where your class of interest is the characteristic in the population is a negative thing, but it's what I'm trying to find. Okay? Who's going to buy my product, or who will give me a good rating, or who will do this or that? That's when the class of interest is positive. Okay? So the naive rule says, take the proportion of your population that are the class of interest. In this case, it's 30%, right? So 30% is the class of interest, and 70% is the non-class of interest. What the naive rule said, if I can see this in my training data, and I have to go to unseen data and make a prediction, and I'm naive, and we hate being naive. I hate being naive, right? Sometimes I am naive, but I hate it when I am, okay? What the naive rule says, if you're stupid, if you're ignorant, if you're naive, pick the word. If you're a dummy, okay, if you have no machine learning algorithms helping you pick these things out, and all you've got to really look at is training data without any algorithms, you could forecast into the future but you do it in a very naive way. So I would take, in this case, I'd say, well, 30% of my mushrooms are poisonous, and if you give me a whole truckload of mushrooms in crates and say, go code them, then I'd say, well, I'm going to predict that 70% of those are good to eat. Since 70 is the majority, then I'm going to say all of them are good to eat. And you should be going, wait, Dean, that's stupid. It is stupid. That's the naive rule. The naive rule says, take whatever is the dominant class and apply that to all unseen data. And you're being very naive. But you're going to be right more than you're wrong, right? You'll be right 70% of the time and wrong 30% of the time, but it doesn't help your customer. It doesn't help you sell mushrooms. Okay? So that's the dumb rule. Okay? So the naive rule is you take whatever the dominant class is, apply it to all unseen data, and you suck. You just did a really crappy job, right? Because with machine learning algorithms, we can go pick the good ones from the bad ones. Yeah.
So when we say it's used as a benchmark, is the benchmark the 70%?
Yeah. Now the benchmark would be we're right 70% of the time and we're wrong 30% of the time. What we want is we want to be almost never wrong. But if you didn't have any machine learning algorithms, this is the crudest way you could do it. It's just really, you know what I mean? This is. I've had students say, well, Dean, why are we learning this? It's dumb. You're learning it's dumb because you're gonna get so much better than the naive rule. That's what we're learning to do in the class. This is the crudest, dumbest way you could do it. But you would be right more than 50% of the time because you just picked whatever dominated and said everything is like that. But then you're like, well, that doesn't help me sell mushrooms. It doesn't keep me from selling poisonous mushrooms, and doesn't help me just sell the good ones. So yeah. We don't like to suck. We don't like that. Okay. All right. Now, the classification matrix is our bread and butter. We use it all the time, and the rock chart. Those are our two ways of looking at classification, looking at model results for classification models and telling whether or not we're doing a good job. And so I'm going to spend the first part of the lecture talking about just kind of helping you see what the measures mean and how this works and how this gets derived. By the time you get through this class, you should just be able to, you can build one of these from scratch. I'll just show you some examples. This stuff will just make sense to you. But it takes a little bit of a soak, for it to just get into your head to where I can just ask you what are the true positives, and you can just say, oh, it's the mushrooms that I said were going to be poisonous, and they are, and so it takes a little bit of soak to be able to do that. Now, in line with my color coding and learning, I've taken the positives and made them green as in go, and I've taken the negatives and made them red as in stop. Again, it's just Doug Dean color coding to help me hook stuff up in our heads. Okay. You'll notice that in this case, we have it going down the diagonal this way. We have predicted going down and up, and then we have the actuals going across. All right. And so in this case, our positives would be we have mushrooms that really are poisonous, and we call them poisonous, and they really are. And then those are mushrooms that we said that they're not poisonous, and they are. So. Or we say they aren't, and they are. Yeah, that's right. I said it right. Okay. So basically, a true positive is, when you look at these, is you're looking down. You look at your predictions are up and down. So we predicted these would be positive, and some are, and some aren't. We predicted these would be no. These would be safe, and some are safe. That's our true safes. And then some are not safe, and we said they were safe. So let me ask you, in the mushroom scenario, what's the most expensive way to be wrong? Yes. Why? That's right. Why is it right? Why is it right?
Because you're telling somebody that it's a poisonous mushroom.
Yeah, you're saying say it's safe, and then they die. That's bad. Okay. Yeah. Some of those. Did I tell you how poisonous some of those mushrooms are? They have some that's called the white angel of death. One killed your collie? Your dog? Yeah, I mean, some of them are just about as poison as you can get. I mean, they're just terrible. Yeah.
So the false negative, false positive, I thought it was not poisonous.
We thought it was poisonous and it's not. Yeah. Yeah, exactly. That's right. So what are you, as a business person, as a businessman or businesswoman, what does this mean for you? You can't sell the poisonous ones because you'll kill your customers, okay? But if you say those are not safe and they are safe, what are you going to do with those mushrooms? You're going to put them in the dumpster, right? You know, I can't trust selling that. So that's going to really cut into your profits because you're going to throw away good mushrooms. So they're expensive both ways. You poison people that you said it was safe. That's the worst one, but you're also killing yourself on your profits if you're throwing away good mushrooms. So there's a cost. Every time you see a red cell, there's a cost. Now, different tools, they'll always give you a confusion matrix, but sometimes they'll put the negatives on the left and the positives on the right. Not a big deal. I'm just telling you that because you just don't just learn the pattern of the positioning. Learn what they mean. You know, it'll always be a positive or a true or whatever. So don't be psyched out when if the tool shows it to you where the columns are just reversed. They're not trying to mess with you. Some tools just show it that way. And so I usually show it to you in one way, but sometimes the tools will just flip those around. All right, so putting some numbers to them there. So if we take this very same pattern and put the data down here, in this case, then these are poisonous mushrooms. There's really 286 poisonous mushrooms in your sample, in your data, and you got 201 out of them. Okay, so you were able to find these, but you didn't find these. That's recall. Recall is what proportion of that population can I find? Okay, so if I'm looking for poisonous mushrooms, what recall is I'm looking for these. What proportion of them did I find? Well, 201 out of 286. That's what recall is. Okay, so recall is this one. You know, we have an actual. What proportion of the actuals are you getting right? Now, Python, scikit-learn, it'll do a recall on the positives and a recall on the negatives. Not a big deal. Still the same idea. What proportion of the negatives did I find? What proportion of the positives did I find? So scikit-learn just shows the recall on both the positives and the negatives. So don't be psyched out by that. Some data mining books, including mine, calls recall on the negative specificity. Don't be wigged out by that. It's just a different word, so you're not using recall for the positives. Okay? So specificity is negative. So specificity is on the negatives. So specificity is we're right 2,689 out of 2,714. So we're right 99% of the time on the negatives. When we say it's a negative, or excuse me, when the negative is in the population, we find 99% of them. Okay? So that's specificity. Then there's precision. What precision is when I say it's a true, when I say that's poisonous, what proportion of the time am I right? These are different, right? It's different than recall. Recall is it really is something. What proportion of those really fine? What precision is I make all of these. I predict all of these are positive. 226 of these I predicted to be positive, and I'm only right 201 out of 226 times. So one is, what proportion that's real do I find? That's recall and specificity. And precision is, when I say it's true, is it true? And what proportion of the time am I right? Yeah.
I thought about how many ducks floated by without you making a guess.
No, the recall would be, of all the ducks that floated by, how many did you find? Yeah, exactly. Okay, so we have precision, we have recall and specificity, and then there is an F measure which takes the average. It takes the geometric average of those. Okay, and you don't need to learn why it's a geometric average. Basically, this average is less likely to be distorted by one side or the other. So what happens is, now we know recall and we know precision on our positives. Okay. And if you multiply those and divide them by adding times that by 2, then it comes up with an average. So here we had our recall, here we had our precision, and this is a geometric average, which is pretty close to the middle. Okay, it's pretty close to the middle of these two terms if you did a simple average. Okay, so basically that. So you'll notice when we were in Python, scikit-learn said recall. It gave us that. And then it gave us precision, and then it also gave us an F measure. And it's just this average across precision and recall, the two most important things that we have. All right, so that's what's going on here. So what I want you to do is get these in your head. You know, in the future, I will help you practice, but I'll say, what's the precision? What's the recall? And I'll give you a little data table, a little confusion matrix, and you should just be able to calculate that. There's probably 8 questions like that on the midterm. Just me giving you data and saying, calculate precision, calculate recall. Which of these are true positive? Which of these are false positive? Which of these are the true negatives? None of it's rocket science. You just got to know it to be able to work in this area.
Do we need to know those measure formulas?
Yeah, you should be able to make the F measure too. Yeah,
Is classification matrix and confusion matrix synonymous?
exactly. They're just 2 names for the same thing. And sometimes I call it, because they're so common, they're both just really popular. Confusion matrix is the same as classification matrix. Yeah. Yes. It's an average. You've got your recall and you've got your precision, and it sort of like averages those two and says my overall goodness of estimating is this. Yeah. So it's a way of just taking an average of those two. Okay. Now, backing up a few slides, we also have accuracy and error. Okay, so if you look at this, then if I say what proportion of the time are we right? Well, Dean, there's 2 ways to be right. We can have true positives and true negatives. So we add our true positives and true negatives, and then we divide that by the overall total, and that we're right 96.3% of the time. We're wrong 25 plus 85 over 3,000, so we're wrong 3.87, which is 1 minus this, right? If you have one of these, you know the other, because it's just the difference between that and 1. So again, it's not rocket science, but it's stuff that, so we'll build models and we'll look at the error rate, we'll look at the precision, we'll look at the recall, we'll look at the F measure. And sometimes our models will just really be fantastic at precision and really crappy at recall. You know, back to the ducks example, it's when I say there's going to be a duck there, I'm right almost every time. But I'm only getting half of the ducks. You know, so you can kind of see that if you only have one and you're not doing well in the other, you still might not be doing a good job. What you really want, when you can get it, is good recall and good precision. Then you're finding everything that there is to be found, and when you say a duck's there, the duck's really there. Now I'm thinking in ducks. Okay? Let's see. Okay. All right. Let's see, we get done at 12:30. Yeah, we're doing fine for time. Okay. All right. The other thing that is behind all of this is what's called the cutoff table. If you remember back to the first day of class, I spent a little bit of time and we talked about the difference between inferential statistics and data mining. Okay, remember that? And I said that a big difference is that we're trying to take every single person and trying to pick if that guy or that girl is going to vote for Trump, right? We're not satisfied with saying the majority will vote for this person or that person. We want to say, for this type of person, are they likely to vote a certain way? And so what we were doing is we're trying to have our data mining algorithms assign a probability that they'll vote a certain way for every single person based on what they look like. Are they old, young, rich, poor? Do they live in the Midwest? You know, do they come from a big family? Whatever. Are they Mormons or are they Catholics? So, you know, we're trying to figure out, based on facts that we know, we're trying to come up with a probability score. Now, in this little simple example where there's only 24, this is a teeny table, but we routinely work with 5,000, 10,000, 20,000. So every single one of those records will get scored with a probability score. I'm sure that's a duck, or I'm sure that's a poisonous mushroom. Boom, it's a 1. You know what I mean? 1 is 100%. I'm sure, okay? Or I'm sure that's a safe one. It's 0. So even though in this one I've shown you 0.99 down to this, in real tables you'll have 1, 1, 1, 1, 1, 1, 1, 1, 1, and then it'll be 0.9999 point, you know what I mean? It'll be sure that it's yes on a bunch, and it'll be sure that it's no on a bunch, and then there's this distribution all the way in between. So don't be misled by the fact, I think I better go rebuild this table and put a few ones and a few zeros in, just so you can say, well, sometimes it really is 1, and sometimes it really is 0, okay? Now, Azure, so we can go show these probabilities in JUMP or Azure. Let me just show you one in Azure real fast. Here it is in Azure on mushrooms, okay? Here it says, yep, that's poisonous. I'm 100% sure that's a poisonous. I'm 100% sure that's edible. But I think that's poisonous, and I'm only 63% sure it's poisonous. So here's an example of it showing the probabilities per mushroom, okay, that of each mushroom that it looked at. And we get these, Python produces this, and so does JUMP as well. I like Azure just because it just makes it so easy to see, and they put little tables in there and stuff like that. But that's what we're after. Okay, now once we get that, then what? Then we go from a table that looks like this to a confusion matrix that looks like this. And this is built right out of that probability table. This was really a new concept for me. I'd never thought about things this way. So, but once you kind of get the hang of it, then it makes a lot of sense. Okay. So what happens is, in this case, it set the probability. All of the data mining tools, JUMP, Python, Azure, they all set the probability cutoff at 0.5. What am I talking about, Willis? Okay. What I mean by that is that they'll say if the probability is 0.5 or higher, predict it's positive. Now, if you look at this right here, it's right most of the time. It said if I set that imaginary blue line right at 0.5, then I said it was positive and it is. I said it was positive and it isn't. I said it was positive and it is. That's a true positive and that's a false positive. That's right. Everything, see, these are actual, but everything above 0.5 we assume is a 1. So we called it a positive, but we were wrong. That's a false positive, okay? So here, in this case, let's build our confusion matrix. Let's build our confusion matrix from the table. Here's our predicted. Here's our 1s and our 0s. Here's our actual. There's our 1s and our 0s. Okay. All right, so where's our true positives in this chart? Right there, that's right, good doing. That's our true positives. Here's our true negatives. Okay, here we predicted it's a 0, but it's a 1, so what is that? Now let's see, let me make sure I get it right. We predicted it's a 0, so we predicted negative, but it's not, so that's a false negative. Okay, we predicted it's a positive and it's not, so that's a false positive. Yeah, we're doing it right. Okay, so now can you build it out of this? Help me build it. So 0.5, so this is 24 observations in this thing. So there's 13 above the blue line. So there's 13 that were predicted positive. So that we know what this is right here. Okay, and we had 2 of them which were false positive, and then we had 2 of them, and then 11 which were true positives. We're actually doing not so bad, okay? Now help me do it on the other way. Below the blue line, we said everything below 0.5 is negative, and we're right all the times except one time. So that 1 represents a false negative, good. So we had 1 false negative, and then there's 11, so that's 1 out of 11, so there's 10 down here. And so that's 11, which adds up to 24. So that's where our math all works out. Okay? So now we could calculate our precision. Tell me how to calculate precision. Just tell me in the numbers. How would I calculate precision? 11 out of 13. Good. It's the number of true positives out of the 13 that we predicted to be positive. Tell me what the recall is what? 11 out of 12, that's right. It's how many of the actuals did you find? Well, we found 11 out of 12, okay? We could have specificity, which would be 10 out of 12, or you could call that recall for the negatives. So specificity is going across this line, and in Python, in scikit-learn, it calls that recall on the negatives. So that's what's going on there, okay? So now let's wiggle the line. Now I'm going to take that blue line. The data in the table is the same. In other words, these probabilities, and whether it's a true or an actual true or an actual negative, is going to be the same. Now let's wiggle the line. Okay, now help me build the table.
Accuracy would have been 21 out of 24, right?
Yes, thank you. Good. Yeah, that's right. Accuracy would, that's right. We were wrong 3 times out of 24. So accuracy in that case was 21 out of 24. And error would have been 3 out of 24. So your intuition is right. Good. Now with the blue line set at we've got the blue line set at 0.75. So now we move that imaginary blue line over here. Now fill out the confusion matrix.
True positive,
7 true positives, 1 false positive. Good. Okay.
5 true, 5 false,
5 false negatives. Good. And then, is that 12? Is it 11? Yeah, I think that's right. Okay. All right. So then we'd have 16 down here. We'd have 8 down here. All right. So, and then, can you see? It looks like you're getting the concept of how to map from that over to here. Now let me ask you the $64,000 question. Let's go back to our mushroom example. Okay. Where would you set the blue line if you're a mushroom seller, and why? Do you set it high or do you set it low? That's right. If I'm a mushroom shop, I would set it at right below the last false negative. I'd set it right there. Because that way everything below that is going to be safe to sell. But I'm going to be throwing away some good mushrooms. Yes.
So, like looking for, of course, like the homework and this and that, like as far as comparing when, like the error rates, this would result in a higher error rate. But
Yeah.
in this business scenario, you'd be fine with it because
It meets your goals.
risk to have that.
Exactly right. Right. If this is good, if the data will only let you be this smart, if the data is only so good that this is what you can produce, you have to do it this way. Okay. Now, of course, I picked a catastrophic place to be wrong. Right. In reality, usually it's sort of like, well, which of these guys are going to renege on their mortgages? Okay, that's your positive. I'm trying to find these people that will bail on their mortgages. All right. And so I would set it higher then and be wrong sometimes because being wrong, the cost of being wrong isn't so catastrophic.
I was going to say, does it just depend on the scenario?
Yes,
There's no magic.
that's right. It depends. There's a payoff for being right and there's a penalty for being wrong, and those vary from situation to situation. So where you set your blue bar is a function of those costs and payoffs. Now later on in the semester, we'll do one where I'll tell you the payoff for being right with a true positive is this. The cost for being wrong for a false positive and a false negative is this. Then we'll go optimize profits based on those payoffs and those costs. So your final homework problem, I have you do that, which is a cool problem. And the other thing is that Azure just lets you drag that blue bar. I love it. Okay. Jump and Python don't make it easy. But Azure, you just literally grab a slider and just slide it around, and your profits. Your confusion matrix wiggles, and then you can map those things down to the money, and you can say, if I set the blue line here, my profits are optimal, and that's really cool. So there's a question up here. I answered it. Okay. All right. So on the exam, I'll give you a couple of these, and I'll say, go build the confusion matrix, and we just did it. You know, it's not rocket science, but it's a new way to think. So just kind of practice and get yourself dialed in. I should be able to go and say, This one that it scored at 0.889, is that, what is that? Is it a true positive, false positive? And you should, oh, that's a true positive. So, okay, all right.